Right.
Hey, uh, hi everyone. Thank you for coming joining us today. We have our guest speaker to our AI seminar, Boyang Li from University of California at San Diego. Boyang Li is a Ph.D. student in Mechanical and Aerospace Engineering at UCSD. Prior to starting his PhD, Boyang received a B.Sc in Mathematics and Physics, double major from William and Mary in May 2022. Boyang has been interested in developing control methodologies that possess both mathematical formality and versatility in application to various robotics processes, drawing ideas from optimization theory, dynamical systems, and machine learning. His research focuses on bridging control barrier functions and Hamilton-Jacobi reachability analysis. And recently, he started to work on safe reinforcement learning ideas with generative policies like. So, Boyang and I have been collaborating on the reduce the reachability project, and yeah, we'll see how it goes. He worked on interesting projects, including the breach avoid and stabilize avoid problem, which has been published in tech research. So I think he can share a bit about past and current research. So please give a round of applause and feel free to take a break.
Yeah. Okay. Thank you for the kind introduction from Professor Nahum Cho, and I'm happy to be here at Seoul National University to give this talk. So this talk is, as Nahum introduced us, is mainly about stabilize, avoid, and reach avoid games. And feel free to interrupt me during the talk if you have any questions. So it's just treat it as a casual discussion along the way. So it doesn't have to be, very formal that you can only ask question at the end. So feel free to interrupt. Okay, so today there are two safety mechanisms that we usually use in the safe control. One is called the reachability, Hamilton-Jacobi reachability. Another is called control barrier function, CBF. And this talk mainly will be focusing on the reachability, but it has connections to CBF. So I'm not sure about the background of the audience. So, but if you have any questions around about with CBFs, you could also ask, and also interrupt me if you have any question. So today, the talk is divided into several parts. And first I'll begin with the background about reachability and another tool called robust control diagonal value functions. And mainly I will talk about three works along this direction. First is the discounted reachability. So basically, we are trying to solve the infinite horizon reach avoid game and the stabilize avoid game. And then we kind of in parallel have a different methods that solves the reach avoid and stabilize problem, but we doesn't need to compute a new value function. We just by composing existing value function and find admissible control sets to do that. So the part one and part two are kind of parallel methods that is trying to tackle the same method, the same problem. And the third part would be a more of using the CLF and reachability for safe planning under disturbances. So first, I will introduce some background and like system definition. So in the talk, we are treating the general nonlinear system, and then we assume it has both control and disturbances. And the disturbance can be adversarial and non-anticipated. So basically, it may react to your control and act in the worst case. So here, oops. So for example, there's a richer white game here that with arrows pointing the direction of the control and direction of the disturbance, and sometimes and basically we assume that we can deal with the worst case. So some definitions here as well. So we assume that our target set T and the basically the obstacle can be characterized by these sub-zero level sets with the functions L and C. And we normally assume that L and C are Lipschitz continuous. And then let's first consider the reach problem. So from here, I will build up the cost and then the value function. So here, let's say you want to reach some goal, and then the minimum of the value, the minimum of the L along the trajectory captures basically when is the soonest time that you reach the target. And then the value function we define here is on both players. So you can think of that your control wants to steer you to the goal, and the disturbance wants to add in the worst case. So the control will take the infimum, and the disturbance would take the supremum. And we can show that in reachability, the sub-zero level set of this value function is equivalent to the backward reachable tube, which means that in the BRT, it collects all the initial states that there exists a control even under the worst case disturbance that can steer you to the goal set, the T. So this is the definition for our value function and why it solves the reach problem. And the natural question to ask is, okay, we have a nice value function, but how do we compute it? And it can be seen that through some derivation that this value function is actually a solution to a partial differential equation with the terminal condition to be the Lx, which is the sign descent function that captures your goal set. And then it can also be cast into this variational inequality form, because if you notice that V can never be larger than L. And then we have numerical toolbox that solves this variational inequality mainly through a dynamical programming method. And here's a video showing that how may it work. Basically, basically you would see that the cyan cone would grow. So it expands from the green side. It just expands and includes more states that can actually reach to your target. So this gives you a visualization of how the value function and the BRT, the sets may look like. And the optimal control is synthesized through the gradient of the value function. And it's you can see that we can handle time variant, both time variant targets, and later you will see we can handle time variant obstacle as well. So yeah, as I said, there are very established numerical toolbox to solve it, but the problem is that it's very slow because we are using dynamical programming to solve it on the entire grid. Normally, we can only scale to up to 5 or 6 dimensionals for the system states. This is called the curse of dimensionality. But in this talk, I'm not gonna introduce methods that trying to tackle this problem, but more on the types of problem that we consider here. Here, previously I introduced how we how we solve the reach problem. But we can also use this Hamilton-Jacobi reachability to solve the avoid problem. So you basically you just gave a sign descent function to your failure set and treat that as the region that you want to avoid by computing all the states that will inevitably hit the obstacle. And then later you can exclude those states. So for example, here in this value function, the L characterize the goal and the C cost characterize your cost, your obstacle. So we remember here we use the convention that negative is good. So here we take the max over C. Can my mouse be shown? Yes. So we take the max here, we capture like the worstest violation that you have, and then we take the max again with L. So it trying to see uh, if there is a time step that I am in the obstacle. So basically, if this max is negative, we know that it is always safe. And if this max is negative, we know that I must have reached. So if this max is negative, we know that both of these has to be negative. So both reaching and avoid are satisfied. And we take the minimum over time, which means that it only needs to happen once. Basically, you only asking, can I ever reach the goal, but not asking, can I reach the goal multiple times? And later we would see that this is the kind of the motivation that we want to develop the stabilize avoid task rather than just reach avoid. So just a recap. So through Hamilton-Jacobi reachability, we get a value function, and from the value function, we can get the optimal control through its gradient. So this gives a certificate function that in your state space collects all the states that can achieve your goal, whether it's reach or avoid or both. Yeah. Yes. So lambda is the disturbance. Some like usually you might see D. Here is stands for the disturbance to be chosen from the non-anticipative strategies. So we use capital lambda and lowercase lambda here. So basically, the non-anticipative strategy, what it means is that if you have two controls, that is identical in the time that are identical in the past time, the disturbance strategy has to be the same as well. So they have to react samely. So here it gives instantaneous advantage to a disturbance to react, but we don't allow it to be, too reactive, that it has to be identical. And of course, there are research on, I think, on disturbances from other policy classes. But here, I think in HJB, we mainly focus on this policy strategy class. Yeah. And then here is, I think, a video that just rotate the value function or the set to show you how the projection looks like. So in practice, the set can be non-convex. So in reachability, we don't need to assume convexity of your target or your obstacle. So that is one nice property. Finally, in the background, I also want to introduce this robust control Lyapunov value function. So some of you may know that COFs are used to certify the stability property of a system, and control Lyapunov function Lyapunov function are to certify the property of the dynamical system, and control Lyapunov value function means that you want to find the control that can stabilize your system. So it's a difference of autonomous system and a control system. But the problem of finding a COF is non-trivial. So in practice, it's very hard to synthesize a COF for nonlinear system. So there are established ways for linear system, I think, through you solve the Riccati equations. But for the nonlinear system, there are not constructive ways. So my previous landmate and my advisor figured out a way that through the lens of the Hamilton-Jacobi reachability, you can actually find a CLVF, which is a CLF-like function, just by solving the PDE. So you have a constructive way to do that. So the idea is that you basically have you put an extra exponential factor in front of your cost function, and the idea is that you exponentially amplify that, and if the value of this CLVF at a specific state is finite, you know that you can stabilize it to the origin. So what it means more concretely is that you have this exponential decay along your trajectory. So you can imagine that the value of the COF value has to obey this exponential decay, which means that every level set of this value function is attractive and control invariant. So one property that I forgot to introduce for the reachability value function is that every level set of the reachability value function is control invariant, but you don't have a guarantee that it would decay to a smaller value. So you can stay within the control invariant set, but you cannot go down. And the CLVF, the reason why it's called a CLVF is that it has an attractive property that if you follow the optimal control, your value can decay, which gives you the stability property of the thing, like it's the thing we want. And then, like I said, it's constructive because you basically are solving the same type of PDE, but with just an extra term in the variational inequality. We will use this tool for the safe navigation task in part 3, I think. Yeah, I think so far these are all the background sections. So if anyone has questions, just let me know. Okay. Yeah. Yeah, it's a good question. I think I made these slides in a hurry, so some notations are not clear. Just feel free to point it out. So basically, uh, you can think of the P as the equilibrium that you want to stabilize to, and if you naively build a sign distance function on P, it won't have this A. So it's you can think of a two norm, a distance to a point. But I think in the computation of CLVF, we actually need to shift this sign distance function down by some positive amount. But I think it's some numerical artifact. Yeah, yeah, yeah. Hmm. Down. Yeah. Yeah, I think it helps with the convergence of the CLVF, but it doesn't change the resulting level set. Yeah. Okay. And oh, another property is that there's a exponential factor theta here, and basically it controls the decay rate. And we have a theorem showing that the the sub-zero level set, which is actually the smallest control invariant set of the system, is invariant to theta. So no, whatever decay rate you choose, the lowest level set, which we call the smallest control invariant set, is identical. So this gives you a design choice that doesn't change the problem nature. And the region of attraction, or the region of exponential stability attraction, is the domain of this value function. So numerically, it means that you can truncate your value function to the place that when it doesn't blow up or goes to a very high value. So the domain is the ROES. So in the first part, I will talk about this infinite horizon reach avoid and stabilize problem using discounted reachability. So uh, so the reach avoid problem, I think I briefly mentioned before. What it means for the infinite horizon reach avoid problem is that you don't need to specify a time that you want to reach to the target. So basically here it means that as long as there exists a finite time t that you are in the target, curly t, while along the way you are stay within the constraint set c, it's deemed successful, this state. So this is the definition of the reach avoid set. And for the stabilized avoid set, similarly, it's an infinite horizon problem because we don't specify when it will. So here we ask it to first reach the target set, and then you want to stabilize to some equilibrium within the target set. So the problem of so the difference of these two problems is that reach avoid doesn't care about what happens after you reach the target. The trajectory may leave the target or may come back later, but you don't know, you cannot tell. And the stabilize avoid problem, it enforces the constraint that you has to uh, asymptotically stabilize within the target, so you won't leave. So these two games are essentially infinite horizon, as can be seen from the problem definition. And also it's a game because you have two players. One is control, the other is the disturbance. And to solve this problem, I think the idea is also, so I think the technique of this paper has been developed, which is the discounted reachability, or in optimal control, like discounting is a popular method. Here we just adopt it to the problem we care. So we found that we can just have a discount factor in front of both like C and L, your reward and your cost. You can have the nice properties that we want. So basically, you can see that first, the discount factor doesn't change the positive or negativeness of L and C. So the set it recovers is the same as if you don't have a discount factor. But discount factor gives you some well-posedness properties, like it gives you a Lipschitz and bounded value function. And more importantly, discount factor is important to have to ensure a contraction property of your value function. Basically, the Bellman operator associated with this value function will be contractive, and then it gives you the uniqueness of the solution of this value function. And later we will show that this also satisfies a PDE. To give you a sense of what it looks like, I think this is a 1D example that x dot equals u. And here we have different gammas. I think here we use gamma. And the solid lines are the numerical solutions, and the dashed lines are the analytical solutions. So as you can see, at least for this example, is almost identical. So the task for this problem is that you want to reach within -1 to 1. This is your target set, basically. And then you want to stay within -2 to 2. As we can show that for this system, actually all the states between -1 and 2 can satisfy the Richard-wide problem. So as you can see that for different gammas, it's sub-zero level set, which are the region below zero, are identical, and they also, all of them successfully recovers the analytical solution. So as I said earlier, that we can also show that these value functions satisfy the Hamilton-Jacobi variational inequality, and it's a unique solution. So I think these are mainly the discounting factor are used to ensure the unique solution, and also the Bellman backup operator is a contraction. Oh, I may missed how I define the Bellman operator, but it's just the dynamical programming principle. I think the Bellman operator is this identical to how you perform dynamical programming update on your value function. And here, by having contraction, it gives us the advantage that you can solve your value function not using PDE, but using value iteration. So you can have some initial guess on your value function, and you just perform dynamical programming update to your value function. Due to the contraction theory means that no matter how the initialization is, you are guaranteed to converge to the unique fixed point of your operator. So this gives you advantage of how you choose to solve the value function. And yeah, it enables you to do warm starting for the sake of convergence speed. So this is for a more difficult example. This is a 3D Dubin's car that you want to reach the green circle but avoid these three obstacles. And we have how the value function looks like for different gammas and also the reachable set. As you can see that they are almost identical. So another discussion we made and a natural question you would ask is, okay, how do we choose the discount factor gamma? So it seems that, and also as predicted, that as you have larger gammas, you should converge quickly as the value decays quickly. So we did some tests, and it is indeed the case. So when it grows, the time for the convergence of the dynamical programming update indeed reduces a lot. But we also realized that there is a problem for having large gammas. So I think there are two problems. First, it relates to how you synthesize the optimal control. So should I go back to previous slide? Maybe. So the optimal control, if you recall, relates to the gradient of the value function. But here, the value function, in essence, doesn't have time inside of the argument. But numerically, to get the optimal control, you need intermediate time slices for the value function. So you need V gamma X and T. So no matter how you pose your problem and define your value function, when you use a numerical solver, it's in essence a finite time problem because you need to back propagate from your Lx and then at each time step one by one, and then you said you got the converged value function when you see your intermediate value function reaches some convergence threshold. So no matter you like here, I may define an infinite horizon problem, but when you put it in a solver, it's identical to how you solve a finite horizon problem. So the takeaway is that to synthesize optimal control, we need intermediate slices of the value function. But if you have a too large a gamma, it converges too quickly that you have very scarce, you only have a few time slices, which means that if you start with in a specific state, you don't have the corresponding time slices for you to synthesize the optimal control. So here we call it the false convergence issue. In the next slide, I think you would see what it means more in a more visual sense. Another is that if you have a large gamma, there's some numerical issue that relates how you update the value along the boundary of your reachable set. So in this figure, it's the same problem as the previous figure that the reachable set should be all the region between 1 and 2. But as you can see at the boundary, there are some states that are not included whose value becomes positive, but they should be part of the reachable set. Although the accuracy is, to a very small number to 10 to the power of -4, 8. So this can be, so the second numerical issue can be avoided if you choose not exactly the zero sub-level set, but some positive epsilon. So practically it's not an issue, but to be rigorous, it's a problem. So there are some practical guideline on how you choose gamma based on the Lipschitz constant of your system. So here, now I move to how do we do stabilize a wide problem. So you may recall that in this paper, we are trying to do both. We are actually, so the motivation was to do stabilize avoid at first. But then we realized that we have to do infinite horizon reach avoid first because we have to, reach the target set first and then talking about stability. So here, once we have infinite horizon reach avoid, it's natural to do stabilize avoid because you just treat your you just first you compute a CLF, so you compute a CLVF from your target set, and here you don't care about safety at all. So you just compute a CLVF and then treat this CLVF more accurately is sub-zero level set as your target for the reach avoid problem. So you first use the previous reach avoid formulation to reach the sub-zero level set of your CLVF, and then you just switch the controller to a stabilizing controller once you reach the level set of the CLVF. So for the stabilize avoid problem, it becomes a two-stage problem, basically by just treating the CLVF as your target function L. And you just compute again. Then you get the desired stabilize avoid set and your stabilize avoid policy. So here you can replace the RCLVF to any Lyapunov function that you already have, maybe from other method. So here we just use the RCLVF for consistency to our Hamilton-Jacobi framework. So yeah. Yeah. I think it's supposed to mean the stabilizing controller. So it may come from RCLVF or others. Yeah. So I think I may not include a figure in the paper that it shows how the value function changes along the intermediate time step when you have different gammas. So there is very obvious to see with large gamma, it converges very quickly, but you lose intermediate time steps. So these two figures shows on the left, maybe it's not very clear enough, but as gamma increases, you can see that at the boundary, there are more oscillatory behavior or an inaccuracy at the boundary. And on the right, it shows the difference of stabilize avoid and reach avoid. So for the reach avoid, it doesn't care about what happens after you reach. So if you continue running your reach avoid controller, it may exit the target set, but it also can comes back because once you exit the set, the gradient tells you to go back again. For the stabilized avoid, we successfully stabilize to the smallest control invariant set within the target. So since this is a Dubin's car example that you have constant velocity, so you cannot stop. That's why on the left, you are basically circling around the center point. Here, you don't have an equilibrium. You only have a set of states that you can stabilize within. So the little squares are to show that with too large a gamma, you lose intermediate value function that is necessary to synthesize the optimal control. Basically, once you run out of your intermediate value function slices, you don't have gradient information tells you what to do. So here we just terminate the rollout. So that's why with large gammas, you have these little squares. So that concludes basically the first part. Uh, it seems I spent too much time, but I'll rush through. No, I'll move faster for the two parts. So here in this work, we consider a similar problem on reach voice stabilize, but it's more complicated in the sense that uh, imagine that we have several goals that we want to reach, but at different time intervals. And we may also want to avoid certain obstacles, but not always, but within some time interval for each obstacle. And ultimately, we want to stabilize to around an equilibrium point. So as you can see, this is a multi-time scale and multi-objective task. So one example is that, okay, you want to avoid obstacle here. You want to first reach the blue and then reach the black and finally stabilize back to the blue, to the equilibrium inside the blue. So this animation is to show what kind of a problem that we want to solve. So the inspiration of this work is that the problem is really complicated and it is hard to define a single unifying value function that captures all these task objectives. So instead, we think that we assume that, okay, what if we know individual value functions for for each specific task? Like we know the reach value function for reaching goal I, we know how to avoid obstacle J, and if we have obstacle that we want to always avoid, we also have this V infinity, and more importantly, the stabilize value function as well. So we basically assume that we get this pre-computed value function for individual tasks, and we want to find a way to compose them to achieve our goal of this multi-objective task. So the idea is that we find the instead of querying or constructing a giant value function, we ask about what are the admissible controls that achieves all these tasks, and we can just take the intersection of them and then doing some verification to solve the problem. So as you can see here, we don't need to compute uh, a new value function, but how do we actually find these admissible control sets? So here you can think that we can focus on just one time step. Like currently I am safe, which means that I have a non-positive value, and then I want to certify whether the next step is safe or not. So basically, you just uh, take the time gradient, time derivative, and you can use some expansion technique to expand the value of your next time step, and then you realize that uh, once you observe this equation, you can see that your design parameters are the controls, uh, are the control here. And if you remove this term to the right, you can see that your admissible controls becomes a linear half space whose inequality is defined by the gradient of your value function and your value function itself. So in a simpler form, you can think of that it becomes a linear constraint on the on your controls. So the admissible control sets becomes all the controls that satisfies this constraint. So when your current state is safe, you can imagine that the admissible control will be the entire control space for your system, because in a continuous time sense, if we have bounded control, you cannot in the next step have a very large value because of the bounded control constraint. So your admissible control set at this moment is the entire control space. But if you're right at the boundary, then the admissible controls are the ones that does not increase your value. So that's why it has this inequality and it's the linear half space here. So if you're already unsafe, and then there's no admissible controls. So here we talk about how do we find the admissible controls. And next we will introduce the stabilized admissible control set and also how to compose them. So here the ACS for the CLVF is similar to previously, but with an extra term on at the end coming from the exponential factor of the CLF. So here you can see that if offline I have I compute the CLVF with a specific decay rate theta, online you can actually choose a theta that is smaller than the what you pre-computed. So although it won't accelerate the decay rate, but at least you have a free parameter here. So in summary, for we have the same type of linear constraint on the controls for all these types of problems. We have finite time reach avoid and infinite time avoid and stabilizing controls. So they are in similar form, and then we can have algorithm to tells you how to compose these. So the input are pre-computed ACS, and or you can characterize this ACS with your value function. So the input can be if you already know the set, or you can just or it can just be your value function. So so the first block is a reach void block. We just so this approach I think is very intuitive and straightforward, though it has its drawbacks. So basically, you just take the intersection of these admissible control sets, and then you forward propagate. You roll out your states for taking by any samples from this ACS, and then you check at the end of the horizon that you cares if it achieves your objective. So you still need to roll out. You still needs to roll out your trajectory. This can be a drawback to our method, and which will be the next step of our research. So basically, if the ACS is empty along the way, you just discard this state. So this algorithm is trying to collect all the states that to find the states that has non-empty admissible control sets to achieve the objective. So if we want to do stabilize avoid, at the end it will be a block that that also do the rollouts to discard the states that violates the constraint. So this algorithm is naturally to see that it's only under approximation of the true reach avoid stabilized set, as we may lose some states by taking random controls within the intermediate ACS. So for the states that we threw out, there might be an optimal control that actually certifies its property, but it's discarded since we are randomly sampled from the ACS. So here's an example of what the set looks like from the animation that I showed earlier. So here we showed two, it's not pretty enough, but here we show two trajectories starting from two initial points. So here, one initial point, we start here. We first reach this blue region, and then we want to reach the black, and ultimately we want to stabilize back to the center of this blue circle. And there are various regions indicated by the dashed lines. They suggest the reachable tube or the avoid tube for individual obstacles or targets. So the second trajectory starts at this bottom, and the task is the same, that you want to reach this circle and then the bottom one and then stabilize back. So here it shows how what the trajectory looks like. And the green region are the certified RAS set. So this, you can see there are some oscillatory or jiggling behavior. It's due to the gradient being not stable. I think this is a common issue for gradient-based methods for the safe control. So we also have another example on the 3D Dubin's car, that you want to avoid these obstacles and these two obstacles. And the goal is to reach this one first and then this one and stabilize back. So in the plot, there's another trajectory that starts close to the boundary, but I didn't have the animation for that. So to conclude this method, we just have an intuitive way to how to compose admissible control sets from individual value functions. But admittedly, this method is not scalable enough that you have to do rollout to verify the intersections won't become empty along the way. And also that it's an under approximation of the true set. Which will be I guess, the direction for future development. And lastly, this project is about, okay, how do we use the reachability-based value functions, especially the CLF, to deal with sudden disturbances for online motion planning. So the motivation is that you have a priori unknown environment. And normally the motion planning framework would give you, so practically for high dimensional system like a drone, you would have a path planning algorithm that gives you a path first, which is blue line, and it might be dynamic, it may not be dynamically feasible, but you would have another layer, which is your actual system. You would run a tracking controller that tracks this planned path, and the safety is normally ensured by building a green region, which is a safe corridor around your planned path and in the obstacle-free region. So this is usually what the motion planning for the motion planning is done. But if you have a sudden wind disturbance that blows your drone off course, the previous method doesn't have a systematic way that tells you how to recover to the safety. And that is what we are trying to solve here. So it's divided into a few parts. The background, so our methods, safe returning fast track, is built on fast track, previous work from my advisor. I will first, due to the sake of time, I will run through these quickly, but these are to introduce different models. So you have a tracker model, can be which is high dimensional and accurately capture your dynamics, but it's computationally intractable. Let's say you have this 5D system and you have bounded disturbances and controls. So your planar model would be a low-dimensional system that might be just a double integrator, but it's computationally efficient for real-time planning. And then you can augment the planar model and compute the relative dynamics for these two models. It's given by the augmented states here R, and its trajectories we denoted by this xi with respect to the R states. So concretely, you can think of that you just have a matrix that augment the planar model into the higher space and just subtract them. And here are the concrete realization of the value of the avoid value function that I talked about earlier. So you define your problem, you define your cost function to be the distance of your the norm of your relative state. So you want to minimize the error, and then which means you want L to be as small as possible. And you just build up the value function here, similar as the same as previous way. So the tracking arrow bound then becomes the smallest level set corresponds to your value function here. Basically, you just find the minimum value of the value function. And the tracking arrow bound is just the level set corresponds to this minimum value. So it characterizes that the smallest possible tracking arrow of the system, given that it may subject to fully adversarial disturbance here. So here we consider two types of disturbance, because one disturbance may comes from the environment, which is this gamma D. Another kind of disturbance is the tracking arrow. So basically, you can think of that in this framework, the planar model is another player that tries to run fast to the goal, which means that it may unintentionally increase the tracking error. So your tracker model is your controlled system that tries to minimize this error. So what the fast track is doing is that you sense the environment, which are these obstacles, and you augment the obstacles by the smallest tracking arrow, by the smallest level set, which is called the tracking arrow bound here. You augment by that, and you plan your run your favorite planning algorithm, RT or A star, within this augmented obstacle-free region, and then you just use your so the tracking control would be from your value function, like the gradient, and due to you run it step by step, and since that you have the guarantee that since the enrichability that your level set is control invariant, so you are guaranteed to stay within certain tracking arrow bound that you start with. So through that, you can ensure that you are always tracking within the obstacle-free region. But there's a limitation of fast track. In theory, it relates to the property that your level set is only control invariant but not attractive. So, which means that if there's a wind gust that blows your true system away from your tracking arrow bound, you only have guarantee that it will stay within, like the relative system is only guarantees to stay within this level set which is larger than the previous TEB, but you don't have guarantee that you will converge back. So it may happen that you will collide with the obstacle when you are trying to when you are trying to move forward. So to deal with this, we basically adopt the previously discussed CLVF to tackle this problem. So specifically, the two types of disturbances that we consider are first, the bounded disturbance directly to the dynamics. Fast track can also do that, but here I just want to clarify what I mean by disturbance. And the second disturbance is specific to this safe returning fast track, that there might be a sudden disturbance that directly changes your states, such as you have a sudden wind gust that blows the drone off course. So for safe returning fast track, the idea is very simple. You just replace your value function, H.D. value function, by this CLVF that gives you attractivity. That then you use RCLVF to synthesize the controller. But you can see that in this way, there's an issue by naively naively replacing value function, that although you have attractivity, but if you don't reset the planner, your relative system are still large when you were just blown off course, and on the way converging back, you may still hit the obstacle. So that brings up a second technique that we use is the reset planner. So I won't have time to go through the algorithm flowchart, but I will walk through the mechanism here. So basically assume that you were here and you're blown off course to here, and then you measure the distance, your distance to the obstacle, and then you find a ball around your true system, which has the radius half the distance. And then we define a safe tracking arrow bound region by, it's small here. So basically, it's the largest sub-level set of your Lyapunov function inside of this ball with the radius half to the distance. And if so we can have safety guarantees if the smallest tracking error bound, the TEB, can be contained within this ball. In the next slide, I will show that if this relation doesn't hold, we won't have guarantee. And we reset the planner to the place that it is in the tracking arrow bound, but it's also closest to the goal state, and it is in the space that is free of augmented obstacle. So what happens next is that after you reset the planner, you run the tracker again, and then you replan from this new planner state. So safety is guaranteed if TB, the smallest tracking error bound, doesn't overlap with the obstacle, and also if it can actually fit into the ball of this radius. Oh. So the intuition is that once you're blown off course, there are two sources of errors that may come from. First is the source that the tracking arrow is one source of error. Another error is that your planner has to have enough distance away from the obstacle for the tracker to converge back. Basically, it wants to ensure that when you're converging back, your trajectory won't hit the obstacle and is done by having the ball of distance to the half distance. So the advantage of safe returning fast track is twofolded. So previously, it shows that how it deals with the sudden disturbance. But when there's no sudden disturbance, it can also accelerate the navigation, which is the second advantage of our framework. So due to the property of RCLVF, basically the attractive property, you can allow your planner to move faster and jump, since you know that you can always converge back. So in practice, it means that you are choosing waypoint in a larger interval compared with the previous method. Okay, so there's a video showing a simulation result of a 10D quadrature, and there will be two disturbance that is happening. So first, there will be a real disturbance that kicks you off course, basically kicks you backward. And the virtual disturbance means that you allow the planner to move faster to show that it indeed can catch up. And the box here indicates the current tracking arrow bound. So that is the STB that we talked about. So due to the attractivity of Lyapunov function, now we can allow variant tracking arrow bound that you would see here. Okay, let's play that. So there are three walls along the way, and it turns red once we detect the obstacle. So this is motion planning in a priori unknown environment. So you don't know where the obstacle are until you sense them. So here, there is a sudden disturbance that when you just passed the obstacle, but you were kicked back, and we need to reset the planner. So this green dashed line indicates the where we reset it. So here, the cyan trajectory indicates the region where we allow the planner to jump to move faster. And as you can see that in the middle here, it realized that itself is obstacle free within the sense range. So it switches to the jumping mechanism. Here, there's a second real disturbance that kicks you back. Yeah, so the bounding box characterize I think we call it safety B. So basically, it's a arrow bound, but it's time variant. Yeah. So the last wall is on this side, so you can get through to the left. And this rotation shows that indeed there's no collision along the way. So to summarize, there are two main contributions. First is that it gives you a mechanism to return to safety when you are blown off course. And another contribution is that it allows you to choose a waypoint smartly according to your ambience situation. So I guess due to the time, I will skip these. But basically, in these three work, we talk about how to do stabilize a wave problem in a rigorous sense. And we talk about a different method that in parallel considers stabilized reach avoid problem using admissible control sets by composing individual value functions so that you don't need to recompute a giant one. And that will be all for today. And these work are all done by with my collaborator Zheng Gong and my advisor Sylvia Herbert. And I would thank to my groups along the way for their inspiring discussions and help encouragement along the way. Thank you. And thank you for the audience and Nahun for attending this talk. Yeah, if any questions, just let me know.
Great.
Yeah.
Is there any questions? Brett?
Mhm.
Uh,
Yeah. Mhm. Mhm. Yeah. 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 I think, yeah, you ask a great question as it's the main issue and unsatisfactory point we had to our algorithm because we haven't find we have we haven't found a way to anticipate where it will be empty without doing any rollout. So here, basically, uh, the the principle is that we don't want to compute any new value function, uh, and other than if that's the case, we didn't see a way of uh, checking whether the ACS will be empty or not without rolling it out, actually rolling it out. But that could be, if that can be done, it will be a huge improvement. Yeah. Mm-hmm. Mm-hmm. C CBF, oh, CLVF, or like the Lyapunov function. Okay. Uh-huh. Mm-hmm. Mm-hmm. Yeah, I think so we here each admissible control set is characterized by a linear inequality, and we are just taking the intersection of the half linear spaces. And I think for QP, if it's a it's a constraint problem, the constraint there, if you are using control barrier functions, it still will be a linear half space. Uh, which means that in essence they are all linear inequalities, and if you take the intersections they should be the same, or otherwise I may miss your suggestions on, are you suggesting that we don't need to take the intersection if we use CBVF QP? Is that what you said, or it's not? Mhm. Yeah. Yeah, definitely. Yeah. Mm, yeah, but I think in that case, you would also have several constraints. Like if we don't compute a new value function, uh, then if you have several constraints in the QP, to solve it, you would still need to, like, at least you need to run an optimization problem online. Uh, I'm not sure if that would be faster or more accurate than ours, but maybe I misunderstood your construction. That we can definitely chat offline on this with some whiteboard discussion, I guess. Yeah, thank you. Hmm. Yeah. Hmm. Yeah. 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 Hmm. Yeah. Yeah. Hmm. Yeah. Yeah. Yeah, thank you. I think it's a very great question because at first I was given, so for at the early stage of this project, my the topic that my advisor gave me is to how do you solve stabilize a wide problem, and then uh, so here, as you can see, we need to have two value functions, right? And it's time consuming. So at first I was thinking, is there a way to use one value function? But the problem is that uh, the role of the exponential factor it plays in the discounted sense is different than the exponential factor plays in the CLVF. So here it's discounting, like it's shrinking. But for CLVF, it's actually amplifying. So here, the time convention might be reversed, but you can check that one exponential factor is amplifying, that is discounting. And due to this contradiction, I didn't find a way to put them into one value function. Yeah. Where is okay. So here, like initially, I was thinking, is there a way to have these one of these to be a amplifying factor? But I failed to prove like such value function would satisfy a PD or even uniqueness. But yeah, I think you right on the spot that found how I got this two step construction. Yeah. Mhm. Yes. Mhm. Yeah. Yeah, definitely. Uh, I think so then it's basically it's about scalability. So uh to for scaling value function, I know there are physical informed neural network pin ways to compute value function for high dimensional system. that basically you cast the PDE into a loss and then as a supervision. And definitely for RL, I'm very so there are already works from other groups that use Bellman update contraction mapping, especially to solve reach avoid problem. So in that sense, and there are several work. I think it's been done for the reach avoid. Uh, but for the stabilizer void problem with only one value function, not two computations with RL method, I think is still open-ended. I think mainly because of how the exponential plays are different. So maybe hard to put them into a single Bellman update. I think that would be the problem. But yeah, I'm curious how it fits into the RL framework. Yeah. Yeah. So yeah, indeed, scalability is a main issue for these safe control formal methods. Yeah. Sure. Hmm. Hmm. Yeah. 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 That's a great question. I think so. Like there might be multi-objective task in the STL sense, signal temporal logic, that you want to, as similar to the problem here, you want to reach in some time, avoid some time, and how to compose this value function together. So I think recently from our group, my lab mate Will Sharpless, he has a work first in SAR last year, but this year, and also RSS this year, in collaboration with Choo Osman. Yes. So basically, they figure out an RL algorithm on how to compose different value functions into I would say like a computational graph. So you can think of each task as a node, and each node can be associated with a value function. And they devise from STL theory, devise a way on how to compose different value function and give you an RL policy, which I think is, for me, is really complicated to learn, but I think it's very powerful way because they have shown that on on real robot demonstrations. Yeah, yeah. I think that could be the topics that you have in mind. Yeah. 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 Right. Yeah. Mhm. Yeah. 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 Uh, I think first some learning methods needs to be done, and maybe RL will be the first choice. Uh, I think there are two different lines. So first, you think about how to compose value functions. Uh, and second, you think about how to, well, for composing value functions, there are, I think, some complicated interplay that you need to consider when you have more than two value functions, several of them, how to, so I think there are many min and max along the way, and it's not intuitive at first glance by naively taking min and max. So figuring out like the logic there is important and may entail temporal logic methods, which I'm not very familiar with. Another direction would be here as what we showed by doing control sets, admissible control sets. So for ACS, I think how to compose different ACS in a scalable way would entail maybe some first requirement on convexity and connectedness of different sets, and basically the geometric aspect of it. But I think the major problem is how do you certify the non-emptiness of them without rolling out trajectory. I think that's the hardest problem, especially in a infinite horizon task involving stabilize. Yeah.
Let's get talk about big hats.